take a look at hypothesis testing, we're going to look at problem 64 from chapter 9. In this example, there have been 7 test subjects who've undergone a training regimen, and we want to evaluate after they've completed the training what their power output is during exercise. And so our random variable that we're interested in is for the subjects being tested, how much they produce during exercise. And looking at the data given, we see that we have a sample of 7 subjects, and the mean output of those subjects during testing was 315 watts, and the standard deviation for the sample was 16 watts. Given this information, we're going to conduct hypothesis testing, and based on the information requested, we want to take a look at mean strength for power generation, whether it exceeds 300 watts. So the parameter that we're interested in testing is the mean of our random variable. And to take a look at the hypothesis that we're trying to assess, we're looking at whether the mean is equal to 300, or as an alternative, whether that mean is greater than 300. The question we're looking at just asks whether it exceeds 300 watts. It does not ask if we are not equal to 300, and so we're going to have a one-sided hypothesis test. In deciding the statistic that we're going to use, we note that we're testing the mean, or mu, in our hypothesis, and our population standard deviation is not provided, and so since this information is unknown, we're going to use the t-distribution. So the statistic we're going to calculate for our sample is x bar minus mu divided by s, the sample standard deviation, divided by the square root of n. Once we've calculated that, we will compare that to our critical value for t, which will come from the distribution. If we look at the distribution, this is our t-distribution, and for the t-distribution, 0 is located at the middle. We are interested in t out at the right end, because we're looking at whether we've exceeded our limit. So we want to make sure that we have something that is above what we would expect. We have 7 subjects, so we have 6 degrees of freedom, and it specifies that we're looking at a significance level, or alpha equals 0.05. And so that means that 5% of the area of our distribution falls above this limit. If we look at our table, we see that the value of t that provides this is 1.943. And so if we go all the way out along our x-axis to 1.943, at that point, with 6 degrees of freedom, we have 5% of the area above that limit. We need something to compare that to, so we calculate a value of t from our sample results. Again, using the equation x bar minus mu divided by sigma over the square root of n. We see 315 is x bar minus our hypothesized value of 300, s over the square root of the sample size 7, and that calculates to 2.48. To make a conclusion about our hypothesis test, we want to consider this value, the 2.48, and the 1.943. We compare those values, and because 2.148 falls above our critical value, we reject our null hypothesis. We have enough evidence that we believe that this is not true, And so we can say, therefore, because of the results of our sample, we do have evidence, based on the question whether there's evidence that leg strength exceeds 300 watts. We do have evidence that is statistically significant that mu is greater than 300 watts. This would be our conclusion from comparing our test statistic to the critical value. Now the problem also asks for a p-value, and we can see the p-value in, again, looking at the t-distribution. We had a value of t that was 1.943, and that corresponded to a probability of 0.05, our 5%, our alpha value. We have for our sample, we have a t-value of 2.48. We come out here along the x-axis a little bit further and find the probability that's associated with that value of t. Okay. This value of t was determined because it did correspond to 0.05. This value, 2.48, corresponds to our p-value, and it is a value of 0.024. We can calculate that by using Excel, the function t.dist, which gives us a probability, but then RT to indicate we want the right tail, and so it gives us the value out here beyond which we have the area beyond that limit of 2.48. Now looking at this problem, let's skip to part D, and it asks how we would do the same conclusion with the confidence interval. To do it with a confidence interval, we need to look at what our confidence, really confidence bound, because we're only looking at a one-tailed test. And given our value of x bar at 315 watts, we're going to calculate an interval. Okay. I'll calculate a lower bound on mu. We want to know, based on our sample, how low could mu be and still give us a reasonable chance at having a mean of 315 watts, given that sample. And our question is, if mu really does equal 300, does that fall outside our interval, or does that fall within our interval? If it falls within the interval, then that means that there's a reasonable chance of getting that the mu could be 300, given our sample of mean of 315. If it falls outside, then that means it's unlikely, depending on what alpha value we've chosen for confidence, it's unlikely that we would have a mu value for 300 when we had a sample of 315. So we're going to calculate this lower bound. We're going to use t again, and we'll see the same parameters we used in conducting our hypothesis test. Okay. 315 is our sample mean. T with an alpha of 0.05 is the same t that we used before. And the same t that we had in our hypothesis test, that was our critical value. If we calculate that out and look at the result, we see that the lower bound on mu is 303.25 watts. So looking at our 95% interval, with x bar equal to 315, this lower limit at 303, mu equal 300 falls down here below that bound. There's a 95% chance that we've got mu in this range from 303.25 up to infinity. It's a 95% chance that given this mean, this standard deviation, this sample size, and 95% confidence, there's a 95% chance that mu is going to fall in this range. Therefore, since it does not fall in that range, then we are 95% confident that mu would not be as low as 300. Okay. So this comes to the same conclusion that our hypothesis test did. Okay, our hypothesis said that there is evidence that mu is greater than 300. Our confidence interval comes to the exact same conclusion, and it must come to the same conclusion because it's using the same sample data, 3, 15, and 16, and it's using the same t-value because we're dealing with the same level of confidence. So the confidence limit that we see here and the hypothesis test that we conducted here give us the same result, and they must give us the same result. So we can use either method to assess this question of whether there's evidence that we exceed 300 watts.